How are you all doing today? I hope you're well. Welcome to week 9. Feels like we're like right at the end of the term, doesn't it? I mean, we are literally at the end of the term. I hope you're all feeling good. This is, I guess, the last week we have of things feeling very serious because you've got your iteration 3 due on Monday, so some exciting times coming up for you. A little bit of a break into week 10, I guess, because once your project's due, it's like pretty smooth sailing till the exam. For week 9's content, we have a few things to chat through. Namely, it's kind of getting into this like loose-ended topics at the moment. So today we're going to talk about software complexity and software safety, and then tomorrow we're going to talk about Git and a bit of a bonus lecture. So tomorrow is going to really be very I don't want to use the word fun, but it's not very theoretical. It's pretty much like, let's talk about Git for 20 minutes and then let's spend some time doing a bonus lecture about building front end. So, and again, the whole point of these lectures in week 9 is that we expect that most students do not come to them because they're bonus, and that's okay because we're happy to have you focusing on your project and have you focusing on your labs, and you're all probably quite tired and all of that. So that's really where we're at. And then next week we'll talk about later. But it's kind of like after today, honestly, for lack of a better phrase, the content's kind of over. It's a lot of bonus lectures for the next few lecture periods, and we chat about the exam next week. So it's all very very manageable. Let's start off today though with 9.1 on software complexity. So I don't think we'll need 2 hours today. We'll see how we go. It doesn't feel like we'll have 2 hours to talk about, but today's topic is all about SDLC design stuff. So, like designing software, and it's about software complexity. And we've kind of talked about this a little bit in a previous lecture where we talk about, keep it simple, stupid, because we want to keep our software as simple as possible. So really, that's all well and good just to say keep it simple, but today's all about how do we talk about how complex software is and how do we analyze how complex software is as well. So why are we talking today? It's, as I said, it's the conversations that matter. We need a constructive way to be able to do that because kind of like, again, I'm sure you've talked to your team members about the complexity of the software your group has written, but it's probably all, most of the time, very much like, oh, this seems really complex. So I want to equip you with the tools to be able to discuss this a little bit clearer. The first one is just to talk about accidental and essential complexity as an idea. This is just really how we talk about different types of complexity, and then we're going to talk about cyclomatic complexity as well. Now, for our 2521 past and present friends, this is a different thing to like time complexity or space complexity. This is not to do with how performant software is in terms of its memory or CPU usage. This is how difficult software is to make sense of. Right, so it's kind of like how the complexity of reading and understanding the code, not the complexity of how fast it runs. So first thing, what is software complexity, right? I know you all have access to the slides, but if I said to, and someone give me an answer here, at least one person. If I said to you, what is software complexity? Like, what is complex software? How would you describe it? Like, I'd be curious what comes to your mind when you think about complex software. Someone says again, what's complex software? Give me an answer. Give you all a short moment to catch up. It's a good question. I don't know if I'd ever have a good answer for it. My answer's probably changed over the years as well, as I've, kind of understood things differently every year. So Hussein says, if you cannot understand it drunk, it's complex. It's not a bad way of describing it, I guess. If you can't understand it drunk, if you can't understand it tired, as a a more universal thing, if you can't understand it tired, it's probably too complex, right? Alex says code that takes a while to understand. Gorb says software that has a high learning curve. to use well. Diorora says convoluted multi-step nested code. That sounds like a thesis topic. Use of hidden lib. I don't quite know what you mean by hidden lib, but I hate the light. If you cannot tell how the backend works. Yeah, I mean, it's not specific to backends, but, you know, if you can't tell how the code works, that's a problem. That definitely implies some complexity there. Now, you know, you're all right, is the short answer, right? There's been a lot of work done in the area of understanding complexity. Kind of the literature that we're referencing here is a fairly old piece of I guess, you know, thought on the topic, which is that the idea of breaking up software's complexity into two types of complexity, which is what we call either essential complexity or accidental complexity. So what are the difference between these two things? Essential complexity is complexity that's inherent to the problem you're solving. And accidental complexity is the opposite. It's complexity that's not inherent to the problem you're solving. So an example of essential complexity is that, you know, if the user or client requires the program to do 30 different things, then those 30 things are essential. You know, you look at your UNSW Streams app, you have all of these different routes in your application that do different things, right? Like sending a message and editing a message and everything else. And it's like, you could argue that having so many routes is an example of essential complexity because it's inherent to the problem. You're trying to solve the problem building the software, and that's inherent to it. Then we have accidental complexity, which is complexity that's not inherent to the problem, right? For example, generating or parsing data in specific formats, writing your own JSON decoder, or doing your own, you know, password encryption. Like an easy way to actually think about accidental complexity is usually accidental complexity in your experiences probably come from one of two places. It either comes from poor use of libraries or poor use of code that was already written, or alternatively, it can come from you just solving a problem inefficiently. And you're probably familiar with that last one, right? You've probably done this with linked lists in C or something similar where you write a problem, it's like 20 lines of code, and then you come back and you write it again later or something, and you can do it in like 10 lines of code. And you're like, oh, I was making that more complicated than it needed to be. So that's really what accidental complexity is. Essential complexity you can't really avoid, and this is kind of why we talk about it, because you don't want to get lost in conversations about how to just totally avoid complexity that you can't avoid, right? Whereas accidental complexity can be mitigated by good engineering decisions. It can be mitigated by design approaches that we've talked about in previous weeks, using things like decorators, all that stuff back in week 5, right? When we talked about dry and we talked about KISS and we talked about top-down design. Because remember, one of the things about top-down design, which is that example where we tried to calculate how long it would take to travel between 2 points, is that top-down design prevents you including code that doesn't do anything, right? So it ensures that like you're thinking very much focused on like what you need. So there are lots of ways we can mitigate this. We can try and remove accidental complexity from your code, but it is hard to remove entirely because, you know, we're all imperfect and we all, you know, write code that's substandard sometimes. So the takeaway here really is that sometimes code is complex, and it's likely that some of that often code is complex, and it's likely that sometimes parts of that, let me rephrase this. Most code is complex, and of that complexity, there's some part of it that's going to be essential. Is that some part tiny? Is that some part massive? That's kind of for you to figure out as a software engineer, right? It's for you to like kind of look at the code and be like, yeah, okay, this looks like it's totally avoidable, or it's not totally avoidable. And, you know, conversations with your group. Sometimes if you're a really good software engineer, you'll write a lot of code that is super not accidentally complex, and all the complexity is essential. Though you can imagine the problems you run into here where, you know, you write code and your team member writes code and they look at your code and they say, oh, this looks like it's, you know, has a lot of accidental complexity in it, and you're like, no, it's perfect. And then you're like, your code looks like it has a lot of accidental complexity in it. And they're like, no, mine's perfect, because we're often terrible at noticing our own kind of mistakes with programming, right? So this is why, teamwork is such a big emphasis, why we try and put so much time and energy into it, is because you need to listen to each other and learn from each other, right? Because it's very rarely are you going to say, well, I identified all of my own problems. This is just a way of talking about it constructively. So questions around complexity: is there a process for distinguishing the two? Not often. It's very hard because, computers, at least, computers aren't super good at like figuring out what's essential and what's not. Usually one of the best ways for distinguishing accidental complexity and essential complexity is just to get more eyes on it or more hands writing it. So for instance, if you have more people writing the code, or they're going to come up with different approaches, and one of them's probably going to be better. If you have more people reviewing the code, they're going to notice the complexity because they're going to read it, and they're going to read it, and then they're going to make sense of it, and then they're going to go, yeah, okay, that makes sense. That's very difficult. Or they're going to go, oh, that's super confusing. And an example of that was 2.5 years ago, I was writing like a calculator. Like I was building an app that was basically there to help you determine when you could retire, right? Like you could take into account your super and your income and your expenses. And we wrote it, and that one's really tricky because there's a lot of math inherent to that problem, but you can also write really ugly code. And we had someone else look at the code, and they were like, yeah, and they went and rewrote it, and it was much cleaner. But as they expanded that out, it got kind of crazy again. And then someone else looks at it, and then they go, oh, okay, I kind of get this. This can be cleaner now. So generally getting more people on there is good. The only other kind of processes that help are just design processes in general. Probably the best way to mitigate complexity in code, in my opinion, is to, schematize, to draw out what you're going to build before you build it. Turn it into a diagram, turn it into a flowchart, document it. Because most complexity, in my experience, with your code, most accidental complexity, comes from the form of you figuring it out as you go. And you know this, right? You know that if you plan to shop for the week and you have a shopping list and you know all the food you're going to eat, you're going to buy exactly the food you need and you're going to eat it like clockwork. But if you're kind of buying little bits every day and you're not really sure what's going to happen, you're going to start having bits of crap over here, stuff that's not used over here, stuff you think you're going to use but don't use because you realize you don't need it anymore. It's the same kind of thing. So planning is probably one of the best ways to get around all of this as a problem. How much of the complexity of modern software is accidental? A fair bit. This is something that I think is the challenge of our time, in the sense that software is so easy to write these days, and there's so many abstractions in our languages that there's an emphasis to get more done. Computer science is more a commodity than a science these days in a lot of ways. So the idea of, we'll write software just because, we can delete it later, or we can change it later, or iterate on it, is quite popular, right? Like, do it, get it done, and then come back and clean it up. That's not inherently a bad thing, though it is a challenge, or at least it brings challenges to the table, because a lot of software that we write, it's complex, and people don't have time to review it or even test it sometimes, which is kind of what the point of this course is about, to help with that. To what degree has or will accidental complexity be removed in the future? This was a question posed by another lecturer previously lecturing this course with me. This is an interesting question. Like, will there be less accidental complexity in the future? Maybe. Don't know. Depends how good computers probably get, right? Like a lot of improving things will probably come from how smart computers can get when it comes to looking at your own code. It's just kind of this weird future that we don't chat about much, but kind of exists, where, you've probably seen this with GitHub Copilot or something similar. It's like computers are getting better at making sense of software. Compilers and linters are more powerful than they were a long time ago, and they'll just continue to get more powerful, and they'll start seeing insights in your code that humans previously were the only ones who could. Can we look at some code examples to analyze? So we're not going to look at some code examples to analyze today per se, though like we could. I might even have a really old file somewhere. Normally, if there's any group in here that wants to volunteer a coding file that they think is like really bad, then please feel free to volunteer yourself, because I'd love to pull it up and we can have like a quick chat about it. That would be cool. But yeah, I'm just trying to pull up something now that I remember from a very, very long time ago. I think this might be it. See if this is it. No, it's not. But that's okay. Does anyone have any any labs they've written that they feel are particularly complex, or does anyone have any parts of their project that they feel like are particularly complex and they want to share with people? Because I would be super interested in kind of seeing that, frankly. Otherwise, we can kind of I might loop back to that, because let's loop back to complex software as we go. If anyone has any ideas, or I'll find some stuff. So the first question was like, what is software complexity and how do we talk about it? That was when we did, accidental and essential complexity. The second part, though, is how do we measure software complexity? So it's all well and good to talk about it qualitatively, but how do we actually measure it? How do we make sense of it quantitatively? So before we get into that, before we get into like the specifics of that, there's two quick concepts that we need to touch on. The first one is coupling and the second one is cohesion. And these are really just kind of some background on how we would kind of think about complexity. This is a little bit more like qualitative, to be fair. Like we say, how do we measure software complexity? This one you wouldn't really get a computer to do. You'd often measure this yourself, though I'm sure there's software out there that can do it. Coupling as an idea in software is how closely different software components, how closely connected different software components are, right? So what that means is like, and you think, what's a software component? Well, think about your project. Now, typically when we talk about software components, we're dealing with like object-oriented languages. Though in this case, let's think about software components as just your different Python files. Like you have your auth file and your channel file and your channels file and your user file and your messages file or something like that. These are different modules or components of your software that help come together to, produce the finished product. And when we look at all of these different files, we could either say that these are loosely coupled, as in they don't really rely on each other very much. They're all quite independent. And we could also say that they're tightly coupled, which is that they all rely on each other. Now, what does coupling mean in practice? The way I often describe it to people is if something is loosely coupled, if file A and file B are loosely coupled, like if your auth and your messages are very separate, then you could delete your auth file and your messages file would still run fine. It's not importing it, it's not relying on it, it's not using tons of functions from it. They're just two totally separate ideas. And a super tightly coupled two components, like auth and messages, if you change much in auth or you delete anything from auth, it'll break messages without making further changes. So that's really the simplest explanation of coupling. Now in software, loose coupling is a good thing, because when we have lots of separate software components, we want them to not be connected, because it makes your code more robust, because it means that you can make more changes, back to our design lecture, without breaking stuff, and that's a good thing. The other idea is cohesion. Cohesion is essentially within a module, how much do elements of that module belong together? So think about your messages module again. You probably got a bunch of stuff in there, like creating a message and adding a message and editing a message. And we want to ensure that those things are related to each other in the same module, because if they're not related to each other, they should be split up. If they are related to each other, they should be combined together. So I'm sure in some of your projects, you probably have a file like other. I think we even made this for you just to get you going. And it's like, you don't, like other.py, if you still have a file like that, is not a great file, because it's unlikely that there's high cohesion between the elements of that module, because you might have something that does this thing and that thing and this thing. So typically you would want to break those up into more files if you haven't already, So if you just have one thing to do with clearing, you would typically have a file called clear, because you wouldn't want that mixed with other things. Because if those other things aren't related, it's what you would say is low cohesion. So if you think about like, the components as your files, low cohesion means that things in there really just are miscellaneous. They don't relate, or maybe they loosely relate. So in this sense, high cohesion is good. We want loose coupling. We want things to not be very much coupled, and within those components that are not very strongly coupled, we want everything inside there to be related to each other, to have high cohesion. And if it's not related, we want to split that up even more. So when the question here, how can we measure software complexity? This is measuring it not in, again, a mathematical way, but more like you can look at someone's code and you can say, this has tight coupling because of A, B, C, and D, and same with cohesion. So you can actually talk about the complexity. This is like a way you can measure it, albeit it's a little bit prone to judgment, it's a little bit qualitative, but a more interesting way to measure complexity, which is somewhat more mathematical, is the idea of cyclomatic complexity. And cyclomatic complexity is a measure of the branching complexity of functions, right? And it's computed by figuring out the number of linearly independent paths through a function. Now, I know that sounds kind of heady, right? Like linearly independent paths through a function. But think about this for a second. When you look at software, what makes it difficult to understand? When you look at a function, what makes a function really difficult? Because it's not the number of lines of the function. I know that we say, you shouldn't have functions with too many lines, but that's just for readability. The main thing that makes it complex are if statements and while or for loops, because they are branches in your code. They are points where you can decide to go here or here. And you know that if you have an if statement and an else statement, and then they both have if and else, and they both have if and else, you've created like suddenly 8 different possibilities of what can happen. Because if you don't have if else statements and you don't have loops, then your function just has one path it goes on. There's no decision making, right? Maybe you have early returns, they technically count as branching, but breaks and stuff count as branching, but you get the idea. It's really those branching elements, early returns, breaks, loops, and as Blake says, conditions that make your code complex in a way we can analyze mathematically. The way that we calculate this cyclomatic complexity, which is just this quantitative complexity that's based on the amount of branching, is we use this function to apply to after we represent our code as a graph. So we're actually going to take our code, turn it into a graph, like a discrete maths graph or a 2521 graph. And then we're going to calculate the complexity like this, where E is the number of edges in the graph and N is the number of nodes in the graph. Okay, so and for some of you who have either probably forgotten about graphs or again aren't too familiar with it, it's like graphs are just a series of circles connected with lines. It's basically a web of stuff. So here is an example of a piece of code, a function called foo that has an if statement in it. It says if A, then we do B, else we do C, and then we do D. So if we were to try and turn this particular code into a graph, this is what it would look like. Now, forgetting how you do that for a second, the graph sure makes sense though, doesn't it? You have A, and then you can either go into the if statement or you go into the else statement, and then they both finish at D, right? Now, what's tricky about this graph, and because I have lots of students come up with different ways of kind of converting this code to this, is sometimes students will be like, oh, well, every function call here I have to put in the graph, or, do I put in the if or the B or the else or whatever. But here's the way to think about it. This literally maps to functions here. And what this means is that whether you enter the if statement or not, you still have to execute this line of code. Right? Because if it's either true or false, but you always execute it. So you're always going to process A, this part here. Then you're only going to process B in some cases and process C in other cases. And then you're always going to process D again. So everything ends up back there. So the cyclomatic complexity of this code here, the number of edges minus the number of nodes, is 2. Right? Because the formula is E minus N plus 2. E, number of edges, there's 4 lines here, 1, 2, 3, 4. And N, the number of nodes, 1, 2, 3, 4. That's the number of nodes. And then you give the plus 2. So now we get 2. Now, because graphs have to have as many, well, I guess something with one node. You can go a little lower than this, like the cyclomatic complexity I think can go down to 1, right? Because if you just have a code that just is like A to B with a line in the middle, E's 1, N's 2, and you add 2 and you get 1. So I'm pretty sure 1's the lowest cyclomatic complexity you can have for a particular piece of software. And it makes sense, right? Because if you have a totally linear function, the complexity is 1 because there's only one like cycle through it. There's only one branch through it. And code like this makes sense that it's 2 because you have 2 different routes through it. A slightly more complex example, I might actually just take this one and like, let's not look at the diagram. Let's just draw this out ourselves so we can, oh no. Yeah, let me just take a copy of this. Right, so we have some code here. Let's like kind of, you know, quickly draw this out ourselves. Now, how might you do this again? Well, you might say up here that, you know, you've got A, because we're always going to have to go through A, right? Because that's like at the start here. And then you've got 2 options. We can either go here or we can go here. Now, where you, like how you label this is somewhat up to you, because obviously in real code, you're not going to have like functions with single letters. So sometimes I like to, you know, just refer to things as like, you know, this here is B and this here is C. As in, like, if I make it into the if statement, then I go to the B part. If I make it into the else statement, I go into the C part. Because you're probably going to want to do this in code that doesn't have those letters. So now I know that from A, I can either go to B over here. Oh my God. I can either go to B or I can go to C. Now what's going to happen here with C? Well, I'm always going to do this part here because I'm doing the if check, and then I'm either going to go to D if I go inside the if statement, or if I don't, I'm going to skip it and I'm going to come back to E here. So the other option with C is that I go straight to E. And you can tell back from this other one up here, once I finish with B, because I don't go through the else, I'm also going to go straight to the E down here. And then similarly, when we finish with D, we're also going to end up at the E. Now, the one thing you'll tend to notice is that pretty much all of these cyclomatic complexity diagrams will result in a starting point and an ending point. I don't think we really do much cyclomatic complexity on functions with early returns. I guess you could. But like generally speaking, if you're trying to look at the complexity of code, you tend not to have early returns, and you tend not to have breaks and continues, because they're essentially they're worse than branching. They're jumping. I mean, they're literal jumps across the program. So you can think of it just with like conditions and loops. So we look at a third example here. Let's have a look at a while loop together. So I'm going to take this piece of code, paste this one in, and again we look at this. What do we know about this code? Well, we know that it's always going to start with A, because every time this code starts, we always have to go through A because it's the first condition to check. Now, what do you know about while loops? Either this while loop checking A will return true because A is true, and if it returns true, what's going to happen is we're going to go and process B. What if A is not true? Well, we're going to skip the loop. We're going to go straight to the end, so we're going to go straight to C here. And what happens if we go inside the loop to B and we finish B here, because it's a while loop, we go right back to the start and we do the exact same thing like this. So now you can look at this and you can say, well, that seems to make sense. So how many edges do we have? We have 3. How many nodes do we have? We have 3. So the cyclomatic complexity is E minus N plus 2, which is equal to 2, right? So the cyclomatic complexity of this code is also 2. Which kind of makes sense because, you know, again, there's 2 different branching factors. You can either go into the while loop, or you can not go into the while loop. That's kind of how the code is reduced to at this particular instance. So looking at the next example, example 4, and this one's more interesting because we don't have the letters, so we'll actually have to kind of analyze this in a bit more detail. We've got this more interesting piece of code here, which is our day to year function, where we convert a number of days in the year, a number of days since 1970 to, it's a little bit Unix timestampy, right? Because Unix timestamps are based on 1970. We convert that to the year. So how are we going to analyze this one? Well, sometimes again it's good to, you could use lines of code if you want to. I'm just going to use letters here. What do we know about this? Well, you can kind of say that. Well, actually, let me show you something. Maybe I will use lines of code to demonstrate something here. So let's actually look at this. We know that we start this program on line 2, right? Because we execute this 1970 year thing. And then what do we know? We know we go down to line 4. So line 4 is the next one in the chain. And then what do we know about line 4? Well, this while loop is either going to be true or it's going to be false. If it's false, we're going to go straight down here to line 13. Sorry, I just can't see behind my camera. Your head's in the way. So we're either going to come straight down here to line 13, or we're going to go to line 5, right? Because we either enter the loop and then we go to line 5. So if we go to line 5, what's going to happen here? Well, we're either going to enter it or not. If we enter it, we're going to go, if we enter the if statement here, we're going to go to line 6. Great. If we don't enter the if statement, that's going to take us straight to line 9. What do we know happens on line 9? Well, if we hit line 9 and we're in this else, then we're going to go straight to line 10. And then we're going to go straight to line 11 as well. I'm conscious that my head's in the way. Right? And then what happens once we get to the end of this on line 11 is we go straight back up to line 4. Like that. So we've kind of finished that side, but let's go back to the 6th one here. When we're on line 6, we're either going to go to line 7 because the if statement's true. So we're going to go here. And then from line 7, we might go to line 8 because that's the next line here. And then after line 8, what happens? Well, we finish this if, we don't go this else, and then we go straight back to the loop. So this one would go, you know, all the way back up to 4 as well. And back to line 6 here. If 6 is false, if we don't go into this if statement, then we skip it, we don't do the else, and we go straight back to the top of the loop. Okay, so now let's have a look at what the diagram actually was. Okay, so there's a bit of a problem here, right? We've got six circles in the answer, but our particular solution here didn't just have 6 circles, right? Hide that background. It didn't just have 6 circles, it had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, one of the cool things about analyzing cyclomatic complexity is that it actually doesn't matter how many circles you draw, because if you draw redundant circles, you actually end up creating redundant edges, and because the formula itself is a linear formula, like this one, if you create an unnecessary node with an associated unnecessary edge, they kind of cancel each other out. So let's actually look at the cyclomatic complexity of this one. How many edges do we have? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I know I haven't arrowed some of these, I'm sorry. So edges is 12. How many nodes do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What's the formula? E minus n plus 2. So we got 12 minus 10 plus 2, which is 4. Did we get it right? I hope we got it right. 4. There you go. Exact same answer. So what's happened in this particular answer is they've just skipped some steps, particularly some of the linear steps, right? So they've said that, you know what, we don't need to actually specify this because I can treat this whole thing as like a single item of work, right? And then similarly, lines 7 and 8 here, we're like, well, I can treat this whole thing as an item of work. So that's an item of work. And I can treat this here as an item of work, the 10 and 11. And in fact, 9 as well, 9, 10, and 11. So you can see here, this could be reduced to one node. This here could be reduced to, well, actually, yeah, this here could be reduced to one node, and this here could be 2. So we could actually take out 1, 2, 3, 4 nodes, which makes sense because we had 10 nodes, and what does the solution have? It has 6. So again, the cool thing about this, because we've seen this taught a few times, is that you don't have to worry about kind of getting it perfect, because as long as you follow the general process, you're going to be okay. right? Like if you apply the rules, it doesn't really matter how your diagram looks, what nodes you have, you'll get the right answer. So that's really cyclomatic complexity. And then let's do another quick example here. Let's do this one, but let's try and be more efficient about it. And for this one, to be more efficient about it, let's just kind of label things. I'll label things with letters this time, just because I know some students like it with letters. Let's call this one line A, because we can tell this is a decision point here. This one's another decision point, line B. Here's another decision point, line C. And yeah, I think that's actually it. Because you might be thinking, well, what about this one here? Should we label this line here, D, for the year? But it doesn't, you can, but it doesn't really need to be, because if you ever reach this line here, right, if you ever reach this line, you're going straight back up to the while loop anyway. So you can kind of lump it all into A, you know? You can just kind of assume that it's all part of the same grouping. So now we can try and draw this out. We say, well, the program starts at A. I might need to label the return D. The program ends at D. And then from A, we either go straight to D, or we come in here and we go to B. And then from B, we either come in here or we go through the else. And then in both of those cases, so maybe I need something else here. So it's like in this case here, we're either going to go inside here to E, or we're going to go through like the C. And again, different students have different ways of visualizing this, but they all end up being the same. So I've got like C and E here. So these are like the two places I can go from the if statement. And then at the end of both of these cases, I'm always going to end up back at A anyway. Now granted, it's a bit of an ugly diagram. I'll admit that. But like, what's the complexity we got here? We got 1, 2, 3, 4, 5, 6. So we got 6 edges. So we got 6 edges, and how many nodes do we have? 1, 2, 3. 1, 2, 3, 4, 5. We have 5 nodes. So that's E minus N plus 2. Maybe I got it wrong. Let's try it out. Should be 3. Okay. There you go. What did they have? They had 7 edges and 6 nodes. When I say they, I mean I think I made this example, but it's like they had 7 edges and 6 nodes. So let's look at what they did what we did differently. So here you can see, here's the starting point. That makes sense. We have that. Then you go to the while loop, which either goes here or here. But there's kind of this unnecessary linear step here. So I'm not 100% sure what this one is. It's probably something to do with in the else case. It's like in the else case we want to go here. This one's probably just doing what I said we wouldn't do actually, which was counting this as a specific node. This year plus equals 1 here, I'm guessing. You can kind of tell when things are somewhat redundant, because they'll tend to only have, well, you'll start to see a pattern where, things flow in a pretty linear format. For instance, these 2 nodes here always go to the same place, and that thing only goes to one place. So like logically, you're like, if both of these go here and here goes here anyway, and it's the only place it goes, it's totally redundant. It's raining. You know what sucks? Before this lecture, I washed clothes, I went to hang it out on the line, and I literally walked back inside, and it, like, I crap you not, it's like 5 seconds later it started raining, so I went out and I pulled them in. And there was a man laughing at me from a balcony, because he just watched me hang out my clothes for 10 minutes and then bring them all straight back in. So in terms of cyclomatic complexity, why do we like it? It's a simple quantitative measure of function complexity. It helps us measure the complexity of functions. Different people have different kinds of, I guess, like opinions on this. I don't talk to people about this extensively, but the cool thing about cyclomatic complexity is you could actually specify a target number. That's like, all these examples we had here were pretty simple functions. But you could say that, no, any cyclomatic complexity that's bigger than, say, 10 is too complex and you're going to have to break up your function. Or you could have something lower or something higher, etc. One of the disadvantages of cyclomatic complexity is that it does assume that non-branching statements have no complexity. Maybe they do, maybe they don't. You probably know this from your own code. Sometimes you'll have very complicated code because you'll be like hashing something and then asserting something and then storing something, and your functions can get very complex very quickly, even if there's very little branching. So that's one drawback of the cyclomatic complexity approach, is that it assumes that if there's not branching, your code is trivial. And as I said, if you keep cyclomatic complexity low, it involves breaking your functions up to solve that problem. There are tools out there for many programming languages that can calculate these for you, right? So there's like a static analysis tool for Python, I believe, that will do cyclomatic complexity checking for you. I haven't used it personally. It's part of Pylint, I see. So I'm pretty sure you can install a Pylint extension. And that Pylint extension will, as part of its linting, do the cyclomatic complexity. Because remember when we did linting, we talked about how linting is both style and semantic. You know, so sometimes you can get all your style right, all the spaces and whatnot, but you can get the semantic wrong. Unused variables, too much, too complex a code. And I think we might have even had a reference to cyclomatic complexity. I can't remember. Let's have a quick look. See if it's there. Semantic issues. Yeah, so it's part of this. So, linting will do some semantic issue checking, bad logic, potential bugs, unused variables. So that's where that falls in. Okay. That's about it. So if you'd like to, take a short moment here to pause the video and leave some feedback, that would be most appreciated. I'm just going to very quickly make sure I have the right lectures for today because we changed them around. Yeah, they're all good. So, yep, if you could leave some feedback, that'd be good. Then we'll take a 10-minute break. I'm not sure. We'll take around 10 minutes. We'll start up at 11 again, and we'll talk about software safety. Which is another somewhat short topic, I guess. So, yeah. Thanks for leaving some feedback and chat. Chat soon.